Hello, this video is going to introduce the TU Delft SDSP course project, Aerial Processing for Communication Systems. We are Zerui and Chenrui, belong to Group 12.1. In short, this video introduces 4 parts: a brief introduction, the mapping between frequency and angle, the MATLAB demonstration, discussion, and brief conclusion. First, introduction. As Lowen, this is a DOA model with 2 sources. The Lowen condition includes the antenna components of this uniform linear array is 5, the receiving signals with complex samples, and the number of sources is 2. The delta is 0.5. The question is to figure out 2 angles. As known from the aerial processing, the model can be extracted as this formula. Figuring out the aerial response vectors is the key point. To solve it, based on spectrum estimation learned in course, we noticed that there is a mapping between frequency and angle, between frequency domain and the spatial domain. Omega I equals to 2 pi times delta times sine theta I. This is the mapping formula, so that we can think of an idea to figure out the angle by spectrum estimation technologies. Then we tested this idea on MATLAB.
Now let's look at the MATLAB code for this project. For time reasons, we will only look at the estimation methods using spectrum estimation techniques. First, we will try to match the frequency domain and the spatial domain using the functions provided in the earlier slides of the presentations. Here, we define the frequency variables omega and the spatial variables theta, and we can match them using these simple functions. Then we look at the Bartlett method for estimating periodograms. We will be given the sample signal vector and the number of segments for Bartlett methods and the number of FFT lengths. And we will use the rectangular windows to estimate the periodograms. So we first calculated the periodogram for every single segments. Then we added them together so we can get the averaged periodograms of the power spectrum. Then we look at the minimum variance estimation techniques. And similarly, but for this, then we will look at the minimum variance estimation techniques for spectrum estimations. First, we will need the autocorrelation matrix of the received signals. Then, we will use eigenvalues to calculate the inverse data of this autocorrelation matrix, and we will be able to calculate the periodogram better than directly calculating the inverse data of the matrix. And finally, it is the music algorithms. In these functions, we will also need additional information for the number of sources and the dimension of autocorrelation matrix. And we calculated the autocorrelation matrix and applied eigenvalue decomposition techniques. Also, we need to sort the eigenvectors so that we can multiply from 1 to m minus num sources, which will be better represented in MATLAB calculations, as shown here. Now let's look at the results from these 3 different functions. As you can see here, all of the three methods have successfully estimated the direction of arrival angles. However, you can see the methods for Bartlett spectrum. The resolutions are not as good as the minimum variance estimations and the music spectrum estimations.
Finally, we can know that the resolution of music is the best. It is larger than MVDR and larger than classical beamformer. And through the mapping formula, we can know that when distance equals wavelength over 2, the resolution is the best. In addition, when the frequency of arrivals is different, there may be an overlapping problem. To sum up, in this project, we figured out the DOA estimation problems using spectrum estimation and have further discussions. For the future, maybe use the general model of winner-receiver to estimate the DOA, or try other promising approaches such as deterministic maximum likelihood and stochastic maximum likelihood. Thank you.